processo, ecco.
Professor?
In genere uno aumenta la, diciamo, fa il window in function alla fine, quando c'ha tutto quanto predisposto.
Ok,
Perché è l'ultima azione che disturba il segnale in modo significativo. Quindi tutto quello che si fa prima e poi alla fine si fa nel tempo, si applica la window e poi si
ok,
risponde.
grazie.
Prego. So your colleague was asking me some clarifications about signal processing. The first one is the zero panic technique, and he asked me about the meaning of introducing some zero and possible effects. If these zeros are introduced with a very low numbers, there is a sort of discontinuity in the signal, and therefore your frequency domain representation of the same signal could be affected that much. Okay, so maybe we can have some errors. If the zeros are in number, a very huge number with respect to what we got, then these effects are, let's say, limited because of the increase of your observation time, and therefore this technique could allow us to have an equivalent increase of the frequency resolution. And the other question was about the usage of the windowing function to reduce the leakage. So generally, we can have these windowing functions that depends on the type of signal that is a constant uniform distribution, that is a stationary signal or a transient. Then we can add, if desired, some zeros, so we can use the zero panic technique, and then we apply the proper windowing function, and then we move to this frequency domain just by taking the Fourier transform. Okay, that is generally the steps that are following. So just before the Fourier transform, we are having the windowing function to reduce the leakage. Any other question? Okay, if not, let's wait for a few minutes just to have all of you join the meeting. How is your laboratory number 1 and 2 and 3? Because I think that by today or maybe tomorrow, I will release laboratory number 4 video recording. Okay. So I would like to have you from your feedback from this laboratory. Did you have the chance to take a look to them? Did you start writing some reports? No feedback at all?
Professore,
Sì?
senta, io ho iniziato a scrivere la prima, però ho avuto dei problemi sulla compensazione perché non ho capito se la curva che lei ci ha fornito
Sì.
diciamo, tiene conto solamente diciamo, della parte quella della variazione della resistenza con la temperatura, ipotizzando che diciamo, la trave sia fatta dello stesso materiale dell'estensimetro. Invece noi abbiamo il materiale che è diverso, giusto? Perché è alluminio.
Sì, allora quello lì tiene conto, diciamo, dei tre effetti, dei due effetti insieme, lascia fuori quello della sensibilità trasversale e quindi
Sì,
anche
quella di quella.
esatto, anche quello del materiale, quindi se vuoi, dove lì è più importante l'effetto, e quindi uno tiene conto della risposta in termini di misura di estensimetro così com'è, va a vedere dal plot qual è la compensazione e poi applica la formuletta per ottenere la lettura dello spostamento, della deformazione così com'è. Se poi dopo ritiene, perché il materiale è diverso, valuta anche come compensare con il materiale, quindi attraverso i rapporti tra le rigidezze trasversali.
E quindi però diciamo, dalla formula che abbiamo ricavato noi a lezione
Come?
ci vede la formula che abbiamo fatto nella lezione sarebbe quella gamma su k più la differenza degli alfa per il delta t. Però se diciamo, quindi nella curva che lei ci dà, il delta alfa sarebbe
Sì.
0 perché e dobbiamo aggiungerlo noi quella parte.
Delta alfa,
Sarebbe l'alfa,
no,
diciamo, del provino con l'alfa dell'estensimetro.
sì, e certo, in questo caso però, siccome lei non ha i singoli componenti insieme, ma il plot direttamente,
Mhm.
o se vuoi la curva,
Sì,
lei lo consideri tutto quanto insieme,
ok,
quindi consideri tutto quell'effetto come una delta epsilon aggiuntivo, come l'abbiamo chiamato,
quindi, ok,
ok? Lo sottrai alla misura fatta e c'ha
sì,
l'epsilon compensato.
ok,
Bene, dopodiché se vede che come si dice, i nu di fatto sono molto diversi tra il materiale di calibrazione e quello che lei sta considerando, a questo punto adotta la terza compensazione, che è il rapporto tra i delta K di fatto da spezzare.
Perché noi diciamo ho provato a fare due calcoli e mi viene fuori che la compensazione dovuta alla differenza degli alfa era confrontabile abbastanza con le misure cioè che
No,
lei ci ha
certo,
fornito.
quindi applichiamo direttamente la compensazione utilizzando il plot. Ripeto, il plot è tutto insieme, ok?
Ok,
Il materiale,
tutti gli effetti insieme.
sì, il materiale c'entra, è importante, però è seconda battuta per quel
Ok,
plot,
perfetto.
ok?
Ok, quindi il fatto che mi venga confrontabile io posso comunque, cioè è una cosa che devo dire a posteriori, diciamo. Prima utilizzo il.
Beh, no, quello diciamo fa la misura,
Sì,
vede l'ordine di grandezza della misura, dopodiché in base alla temperatura operativa va a vedere quanto sarebbe la compensazione attraverso l'impiego del plot di compensazione.
sì.
E a questo punto, guarda, la misura e la compensazione sono dello stesso ordine di grandezza, vale la pena farlo. Se invece la misura fosse stata di un ordine di grandezza, due ordini di grandezza più grande, a questo punto è inutile che mi porta appresso la compensazione.
Va bene, ok. No,
Ok?
perché il dubbio mi era venuto perché, diciamo, sulla tabella che ci ha fornito lei ci stava una X sullo still, e quindi pensavo che la compensazione, diciamo, di quel plot fosse, considerando che l'estensimetro era fatto di acciaio e anche il
No,
provino.
no, l'esensibile non è fatto da acciaio, è il
Sì, no,
provino,
scusi,
cioè
no,
il materiale di lavorazione. No, no, certo,
sì,
è
sì, sì.
importante quello, è chiaro, però sta bene la teoria, quello che poi dopo serve è la differenza dai coefficienti di Poisson, no?
Ok,
È quello che fa grossa differenza. Allora, nel plot viene messo tutto quanto insieme gli effetti più importanti. Il materiale, quindi i Poisson, vengono messi dopo con la sensibilità trasversale.
va bene.
E
A
tutto
posto,
ovviamente
grazie.
ha a che fare con la misura di riferimento, cioè quello che lei ha misurato senza nessuna compensazione.
Ok,
Va bene?
va bene, grazie.
Ok. Another question was about the temperature compensation regarding laboratory number 1. Your colleague was asking about the material effect because in the compensating chart there is an explicit reference to the calibrating material in the with the strain gauge that we use. The calibrating material was steel, whereas the beam was made by a light alloy, maybe aluminum or something like that. So your colleague were asking whether or not he should include also the material effect and therefore the ratio between the transfer sensitivity. The comment that I made is that that plot is taking into account two effects out of three, and those are the most important effects that you have to take into account. The third one, the material, is also included, but you have to add the last equation that I gave you during the class that takes into account the transfer sensitivity. So first step is apply the compensation from the plots from the compensating chart, okay, and see what is the magnitude of this compensation, and compare this magnitude with the measured one. If there is a big difference, that is the measured one is one order or two order higher than this temperature compensation, maybe you can forget about this compensation in order to have a fast evaluation of your result, okay, without suffering too much inaccuracy. On the contrary, if your measurement is of the same order of magnitude than the compensation that provides your temperature, then you have to take into account this compensation. The material compensation is second order if you want for our analysis, so you can take into account after that if you want.
Professore,
Yes.
se posso, credo che ci sia stato un equivoco dovuto al fatto che nella traccia dell'esercitazione 1 lei ha messo un estensimetro appunto dove il materiale calibrante era l'acciaio, però in realtà nella prova ha utilizzato invece un estensimetro calibrato con l'alluminio. Infatti i dati sono
ok, quindi
forse è per quello che, perché anch'io avevo avuto questo problema, però poi guardando attentamente proprio la registrazione si vedeva proprio che veniva utilizzato un diverso strain gauge factor di 2,1, invece quello riportato sulla traccia era 2 e anche il datasheet era diverso, quindi per quello io ho usato quello del video, diciamo.
Va bene lo stesso. So your colleague is pointing out that the strain gauge that I used during the video recording is different with respect to the one that I consider in the text of the laboratory activity. The one that I used in the video recording was based on the aluminum alloy. The one that I reported in the text is on the steel one. Okay, you can choose the one that I declare in the video recording, so don't worry about that. But however, the way to proceed in these cases, that is when you are using a strain gauge that is calibrated on a different material, is the same that I gave you before, that I discussed with you before. Okay.
Ok, magari quindi possiamo aggiungere nel report, ad esempio io che ho utilizzato quello con l'alluminio, potrei aggiungere quale sarebbe stato l'effetto, quindi l'errore di calibrazione nel caso in cui avessi utilizzato quello con l'acciaio, giusto?
Sì, se vuole, sì.
Va bene, grazie mille.
Prego. So if you want, you can just add a note in your report pointing out that you are using one data sheet with respect to the other one, or what could be different temperature compensation using a different data chart with respect to the one that you use. Okay, so it's up to you. Okay, let's start our class. Okay, during the last classes, we saw some estimating methods for the model parameters that are based on the multi-degree of freedom system in the modal domain. We saw a general frequency domain-based approach. Then we saw the one time domain approach that is called complex exponential method, the square complex exponential method. Now I'm going to discuss with you another time domain technique that is called Ibrahim time domain technique. And this time domain technique is very interesting because the estimates start from the evaluation of the free response of your system, and it is quite robust with respect to the presence of noise. So I can write that. So modal parameters from free response, and this approach is robust with respect to noise. Okay. One question could be that we are not always having the free response handy, because maybe we are exciting the structure with a shaker. And therefore we can assign a structure with some random excitation, stationary excitation, so we are not available the free response. However, please remember that once you have estimated using, once again, your H1, H2, or HD estimator, okay, your frequency response function, then you can go back in time domain, and therefore you have the impulse response function, and therefore this impulse response function is equivalent, as we already discussed, to a free response. So you can use your Ibrahim time domain technique regardless the type of excitation signal. However, this technique was made by thinking at a free response. So the earlier usage of this technique was just exciting the structure with non-homogeneous initial conditions and recording the free response. Okay, but however, with the availability of the frequency response function, we can just have the requirement to go back in time domain, and therefore we can use the impulse response functions as the equivalent of equivalent functions representing the free response. Okay. Then our free response could be written in terms of the output in a specific measurement point that is your whatever degrees of freedom from the analysis. Okay, so what we can write is that your whatever ith response in time domain, okay, could be written as your summation sign goes from 1 up to the number of moles. Please note I'm using 2m because it could be complex conjugate parts. Okay, then your modal contribution, that is your residual part if you want in the frequency domain, okay, times the exponential part that takes into account your pole. Okay, and of course your I index is going from 1 up to the number of output that you are going to record your responses, or you have in your frequency response function from your impulse excitation, whatever it be. Okay, and that is your response time domain response. Okay, evaluated at the ith degree of freedom. It is your whatever measuring point that you are using. Please, this degree of freedom is experimental. Okay, let me write that, experimental degrees of freedom or measuring point. Okay, now, because you know very well that we are not going to measure a continuous function, but we are living in a discrete world because we are having a sampling time, okay, we can rewrite the same response of the ith degrees of freedom that is evaluated at the jth time domain sample. Okay, so we can rewrite that as your response of the ith degrees of freedom at the time tj. Okay, and so what we got is your xij indexes that are set equal to this summation sign. It was just equal to the same one that we already discussed. So R corresponding to the ith degree of freedom, lambda R tj. Okay, and in addition, your j subscript is going from 1 to up to the number of sampling points in time domain. Okay, and S is sampling point, of course. Okay, now what we can say is that why don't we build a matrix of these free responses, okay, of your system, that is your xij could be considered as elements of your response matrix. Okay, so I can build the matrix of the responses as this matrix. That is your x1, t1, x1, t2, okay, up to the last one, x1, t, t, and s. Then the second row is x2, t1, x2, t2, and then up to the last one, t and s. And then if we are having, let's say, general x2 m points, okay, t1, x2, and t2, up to t and s. Okay, we call this matrix of the responses as the chi matrix. Okay, so let me recast all of these responses as the elements of a matrix. That is your chi matrix. Okay, that is by definition that matrix. Please note the dimensions of that kind matrix is in general the number of measuring points times the number of sampling points, and s. Okay, so if we are setting the number of sampling points that are used to build this matrix equal to 2m, that is the order of your system, okay, and if you are considering that your number of output points is 2m once again, then your chi matrix is a real matrix whose dimensions are 2m times 2m. Okay, so it is a square matrix. Now, as you can figure out from now on, I am assuming that I know what is this number 2m. That is the order of your system in the modal domain. If you go back to the very first equation that I wrote, m or 2m, if I'm considering both complex and conjugate parts, is representing the number of modes that I am considering to build your own response. Okay, so actually also the number of modes is an unknown quantity, as we consider when referring to the least square complex exponential method that we already see. Okay, so by now let's assume that I know this number of modes so that I can start my procedure. And as you can imagine by yourself, in order to solve for this unknown number of modes, you have to introduce your stabilization diagram also for such a method. Okay, so let's assume that by now this hypothesis is good, that is the number of sampling points that we are using is equal to the number of output that is equal to the order of your system 2m.
Excuse me, Professor. So
Yes,
I didn't understand. We consider that the number of modes are known. I mean, we know the m number.
no, we don't know them. In general, we don't know, but for the procedure, I am assuming that I know them. Okay.
Okay, like the matrix that we found.
Yeah. Okay.
Thank you.
Just in the same way that we consider known the number of modes, we're referring to least square complex exponential. That is the previous approach. Okay. Okay, so if that is true, we can also define what we call the modal matrix. Okay, is defined as your modes that are all in columns, as always we are considering them. So what we are having is the first component, first mode, second component, second mode, up to the last one, and O times, sorry, we have the same mode here. Okay, then first component, second mode, second component, second mode, last component, and O of the second mode itself, up to the last one, first component to M, okay, and this modal matrix is a psi matrix, okay, that by definition is built as it is. And of course, we are also assuming that it is assumed that we are having that the number of output is equal to 2m, as we did before. Okay. Finally, we define the matrix of the natural frequency lambda, bold capital lambda, in this way. So the matrix so E to lambda 1 T1, E to lambda 1 T2, up to the last one, E to lambda 1 T and S, then E to lambda 2m T1, E to lambda 2m T2, E to lambda 2m Tms. Okay, and this matrix of natural frequencies is your capital bold lambda matrix. Okay, that is defined in this way. Now, if you compare the previous equation that is giving you the time responses, here it is, okay, with these definitions of the matrix, we can have a more compact way of expressing your free responses, evaluating at the ith degrees of freedom at a given time instant, Tj, using those matrices in this way. So the free response could be written as your chi matrix equal to your psi matrix times your capital lambda matrix. Okay, and that is your first equation that you have to consider. Let me call that equation A, because I will need it later on. Now, the method is redoing the same evaluation of the time responses as we already did, but using a time shift, a different time sampler as the first value that we are considering. So instead of using your t, that is your previous analysis, we shift that to a different t, let me call it t star, that is equal to the previous one plus a time shift, let me call that delta T1. By now, it is important to consider that this time shift must be in general different from your sampling time, okay? Okay, delta T, just to be sure that we are considering a different number than the one that has been sampled. And therefore, because of that, the new responses could be written as your response. Oh. Okay. Your response, free response, corresponding to the I degree of freedom at this new time value, time star value, as your xi, that is your tj plus delta t1. Okay, let me call it tj, whatever. And therefore, by introducing the pre-representation, that is the link between the responses and the model parameters, that is equal to the summation psi from R1 to 2m phi I R, that are the same, and that is equal to E lambda R time I, sorry, plus delta T1, sorry, time J. Okay. Now, we can call this quantity, okay, the response at a time shift delta T1 as your hat ij quantity. Okay, so that is the definition that I'm just considering right now. And also this quantity, the quantity that is in the summation sign, could be reviewed as your hat psi I, corresponding to the R node, that is equal to the psi I, corresponding to the R mod, times your E to lambda R delta T1. Okay. By introducing this way of evaluating model parameters, we can have that your time response at the time shift delta T1 could be written in a compact form as so up chi is equal to psi up psi, sorry, times the same large lambda both lambda matrix. Okay, and this important relation could be named as the B equation. Okay, please note that your chi matrix, okay, is having the same structure as we already discussed, that is equal to x1 t1 plus delta t1 up to the last point for that row, t and s plus delta t1, and then to the end x2m t1 plus delta t1 x2m t and s plus delta t1. Okay, and your psi matrix is having the form of, for example, phi 1 e lambda 1 delta t1 phi component 2m same vector 1 e to lambda 1 delta t1 up to the last component phi 1 mod 2m e lambda 1, no, sorry, lambda 2m delta t1. Right now, delta t1 psi 2m mod lambda e to lambda 2m delta t and s. Okay, and that is
Excuse me, Professor. What?
just one sec.
Why?
Just one sec. Okay. So say your question.
Why they are not in the phi e to the power lambda 1? Why there isn't t plus delta t?
Because we already take into account in the e to lambda that are here. Okay, if you consider the definitions of lambda that I'm going to write now, I already wrote another, place it here. We got in the large bold lambda the information of the time shift, okay, of delta t1, 2, and so on. So what we got is just a time shift in the phi vector, matrix.
Okay, thank you.
Remember, your lambda, bold lambda here is having your time counter, t1, t2, and so on. Okay, whereas the hot psi is taking into account the eigenvector, okay, and your delta t. Okay, delta t1, that is your shift, time shift. Okay, so as a matter of fact, both your responses that are all recasted in the chi matrix and your responses that are recasted in the hot chi matrix are built from the recording of the time responses, okay, at different time instants. Okay, so all those quantities are available because we are having those information. So what is written in the chi matrices, regardless if they are the chi matrix of the hot chi matrices, these are quantities that are available from our experimental analysis. Now, from equation A, that is this first one that we consider, okay, right, the expression of the large bold lambda in this way. So large bold lambda matrix could be written as the inverse of the psi matrix times your chi responses. Okay. Then substituting it into equation B, what we got is that your hot chi matrix is given you by your psi matrix, hot psi matrix times your psi matrix inverse times your chi matrix. Okay, and that is a very, very nice equation. Okay, we can call that as square equation. Okay, why that is important? Because it gives the relation between the responses at different times. Okay, the hot, remember, the hot chi matrix is the response that we are having by time shifting of delta 1, okay, your hot time response. Sorry, your chi time responses, okay? And if you want, that equation could be rewritten in this way. Okay, thus by defining your A matrix as your hot psi times your psi to the minus 1, we can have that your hot chi matrix is equal to your A matrix times your chi matrix. And that is very, very nice, because that is the magician's equation. Why it is the magician's equation? Because if you are the magician and you know the matrix A, then you can predict the future just by knowing the actual response. Okay? Because if you apply your chi response to the matrix A, you can predict what happened to the system when you are considering a time shift delta T1. Okay, and because of that, we can say that the matrix A, it has the very well-known meaning, and you should know that is your state transition matrix. Okay. I hope that you saw many times this state transition matrix when you were preparing the Battilotti's course. I hope so, of course. So the state transition matrix, that is, it relates the state vector from one point in time domain, of course, to another one, to the next one, actually. Okay. And as you know, because of that, also the matrix A, the state transition matrix A, contains the unknowns of the problems, or the problem that we are considering, that is your modal parameters. Okay. And that is very interesting because it can be derived from the free response, that is from the chi matrix. Okay, and that is the other important story. Can you see the point? Let me repeat that once. Please remember, we start from the very beginning with the relation between the free responses and the modal parameters. By the way, we are not considering any participation factor. They are included in the modal amplitude. So when I'm writing phi matrix, then we are phi vector or phi matrix, then we are considering also the participation factor. Okay, so let me add your phi is including the participation factor. So the scaling factor and whatever. Okay. So we start from that. We define two, if you want, dummy matrices, the psi and large lambda, both lambda matrices that are having the eigenvectors and the eigenvalues of your system. And then by using this, the expression in the actual time response and the one that could be obtained by time shifting of a quantity delta T1 to be specified later in our analysis, we can have an Hart-Kai matrix of responses, and by comparing these two relations, A and B, we can say that your A matrix, that is your state transition matrix, is relating your actual response with respect to the next one by time shift delta T1. So by using this equation, we can have the information of the model parameters, and therefore we can estimate your model parameters just by knowing the output responses. Okay, now before going on with the this evaluation, let me see why there is why all our unknowns are known once we know the A matrix. From this equation, so from the definition of the A matrix, then what we got is the psi matrix is equal to A matrix times psi. Okay, and because remember we say that the Hart eigenvector, let's say R eigenvector, is obtained from the corresponding eigenvector at the time shift delta 1, so it is equal to E to lambda R delta T1. Okay, therefore by plugging that into the first equation written by columns, what we got is psi R E to lambda R delta T1, okay, is equal to A times psi R matrix. Okay, therefore we can rewrite that equation as A negative E to lambda R delta T1 times psi R, and that is equal to 0. So as you can see, once we know the A matrix from the eigenvalue associated to the A matrix, we can have the estimate for our model parameters psi and lambda. Specifically, because we are having that your psi r is your phi r, okay, by definition, or the column, the rth column of the psi matrix is the rth eigenvector, and we build that in that way. So the previous equation could be written as A negative E to lambda R delta T1 times phi R equal to 0. Okay, so what we got so far is that the eigenvector of the state transition matrix A are the system eigenvectors. Okay, and that is the first. The system eigenvalue is linked to the eigenvalue of A, okay, through this equation. Let me call this equation the eigenvalue, the Rth eigenvalue, that is generally a complex quantity, is equal to e to lambda r delta t1. Okay. So the system the eigenvector of A are the system eigenvector. So they are representing our unknowns. But when referring to the eigenvalues, we are not at direct information, because the eigenvalue of lambda, the direct complex quantity, are related to the exponent of the actual eigenvalue of the system. Okay. Now, let me see now what we can write with that. Because we are having that the e to lambda r delta t1 could be rewritten as e to the real part, remember, plus j omega r delta t1. That could be rewritten as the real part and the oscillatory part in this way. Okay, we are having that your eigenvalue of A that is having a real part AR and an imaginary part BR is related to the system eigenvalue through this equation. Okay. That is, remember, the eigenvalue of A. Okay. So although the eigenvector is straight the information that we want in terms of the eigenvector of the system, the eigenvalue of A is related to the eigenvalues of the system through this equation. And therefore, what we can say is that AR is equal to E to the sigma R delta T1 times cosine omega R delta T1. The imaginary part, BR of your eigenvalue of A, is E sigma R delta T1 sine omega R delta T1. Okay, and therefore we have the estimate of our poles of the system, okay, that are your sigma R part is 1/2 delta T1 logarithm of the square of the amplitude of the eigenvalue of A, whereas the omega R, that is the imaginary part, is 1/delta T1 R tangent of your imaginary part over the real part. Okay. And that is what is happening, okay, when we are having your information concerning the matrix A. Now, how the matrix, this state transition matrix could be evaluated. So how A is evaluated. And that comes straight from the information that because we got that the hot chi matrix is equal to A chi matrix, then your state transition matrix is given you by your hot chi matrix times your chi matrix to the negative 1. Okay. Please note that the inverse of the chi matrix could always be carried out because time responses are linear independent with respect to the time shift delta T1. We have an exponential decay. So what we can say is that if you compare two rows or columns of the chi matrix, therefore these two columns, because of the time responses, also because with respect to the time response, not delta T1. Shift at the time. Okay. If you compare these two rows or columns, because of the exponential decay, they are not linear independent. Therefore, we can always perform that matrix inversion. Okay, and therefore we can have an estimate of it. So let's recap the approach so far. We start from the recording of the free responses or from the inverse Fourier transform of the FRF that have been obtained from H1, H2. Then we use the model that links these free responses to the model parameters, the one that I just displayed now on the screen. Okay, that is the model combination of the model vectors and the eigenvalues. We build the chi matrix, we build the modal matrix, we build the modal natural frequency matrix in the way that I showed. Then we consider a time shift, and that is the peculiar thing of this approach. Because we are a large number of time samples, then we can assure that there are lots of responses that are allowing us to consider a time shift delta T1 to be used to rebuild the new matrices that we call hot chi and hot psi, as we defined before. Then by just comparing these by comparing these chi and hot chi matrices, we can say that the state transition matrix A could be estimated just by using the time responses and the relation between. So we can use this equation. So that equation, so this equation is used to estimate A. And then once we are having A, the eigenvector corresponding to the standard eigenvalue problem associated to A are just the system eigenvectors. So it is the first set of unknowns that we know. Then the eigenvalues are derived from the eigenvalues of A using this equation. Okay, so the real and imaginary part are here reported as expected. Okay, so another important thing is that what if we are in troubles in making the matrix inversion? Remember, in every procedure that requires the matrix inversion, you have to take special care of this numerical operation, because the matrix inversion could be done if we can do that. And in our analysis, chi to the minus 1 could be always carried out because the rows and the columns of the responses, matrix of responses, are always linear independent. There is an exponential part that allows me to say that there are no linear dependencies between rows and columns. And therefore we are very happy because we can always estimate your state transition matrix A just by the measurement of the responses as we discussed so far. Okay. Okay, that's it by now. Let's have a 5-minute breaks, and then we resume the class with additional discussion on this method. Of course, if you have questions, just show them.
Professore, scusi,
Sì?
credo di essermi perso una definizione, ma l'estimatore HT, quale sarebbe di quelli che abbiamo visto?
Sta nel laboratorio 3. È una via di mezzo tra H1 e H2. Un po' più complicato.
Ah, ok, va bene, grazie mille.
Prego.
Professore, scusi,
Prego.
ma domani ci sarà lezione oppure no?
No, domani è festa, no.
Ah, va bene, grazie.
Magari ricordami alla fine, ma insomma era mia intenzione informarvi alla fine della lezione.
Va bene, grazie.
Prego.
It turns you into a macho.
ये तो बड़ा टाइम है.
Really? So that specific clothing turns you into a man. Okay.
तो पापा को फोन लगा. हेलो पापा, हेलो बात करो. हेलो सर, आपके बेटे ने सिग्नल तोड़ा, फाइन तो लगेगा. नॉनसेंस, एक पैसा नहीं दूंगा. अंदर डालो उसको, तभी सुधरेगा. सर सिग्नल ही तो तोड़ा है, कोई होमोसाइड थोड़ी किया है. तो फिर एक थप्पड़ मार उसको. लेकिन सर लड़का इतना बुरा नहीं है। बुरा नहीं है तो तुम पालो।
आ रहे हैं पापा।
जा
पापा थैंक्स हाँ।
जब लाइफ दिलाए जाए
It was him.
I was him.
Oh my gosh. Oh, that's hilarious. What the hell?
Oh,
बेटा मन में लड्डू फूटा, नया कैडबरी डेयरी मिल्क शॉट्स, चॉकलेट और दूध के लड्डू। बेटा मन में दूसरा लड्डू फूटा, नया कैडबरी
Did
डेयरी
you
मिल्क
see what he's
शॉट्स,
done?
2 रुपए में 2 लड्डू, कुछ मीठा हो जाए।
Oh my gosh.
report one.
Wow.
Report 2. But sir,
Shut up!
sir, hotel reservation desk on line 2.
Yes, I would like to book a table for 2.
Sure, sir.
Poolside.
Your name, sir?
Hari Sadu.
What, sir?
Hari Sadu.
sir, may I? Yes, write down Hari Sadu. H for Hitler, A for arrogant, R for rascal, I for idiot. That's right. Now write Sadu. S for
India's number one
shameless.
job site. Oh my god.
Raja?
क्यों मजा आया? कुछ चीजों का मजा धीरे धीरे ही आता है, जैसे कैडबरी एक्लेयर्स क्रंच, क्रीमी कैरमल को धीरे से खाओ।
Oh my
फिर
god.
So
धीरे
random.
का मजा
Okay,
It's so
uh,
random.
now
so
let's
cringy.
resume the class and let's see what's happening to this method when we are not dealing with a square matrix. Remember, we assume that the number of sampling points and the number of outputs that we consider to record your responses, your free responses, was set equal to the order of the system, that is equal to m. Now, let's remove this hypothesis and let's see if we are having that the number of sampling points is larger than the order of the system, the model order of the system 2m. And let's assume that your number of outputs is still equal to n. Okay, what does it mean then? If you remember, if you consider your chi matrix, for example, that was a square matrix like this. Okay, in which we are having a 2m times 2m matrix. Now, if you're having that the number of sampling times is larger than the 2m, that is, your chi-matrix is something rectangular of this shape. Okay, this is just a, let's say, geometric representation of how these dimensions are. So it would be 2m times ns, being ns larger than 2m, this kind. Okay, so if that is true, so your A matrix, remember, that is equal to half chi matrix times the inverse of the chi matrix. Okay, could not be obtained. Okay, because in general there is not a chance to having the inverse of a rectangular matrix. Okay, however, by multiplying that equation, okay, by your chi transpose, what we got is the following equation. So what we got is not just, I'm sorry, multiplied by k matrix and taking the transpose, what we got is chi transpose A transpose equal to chi transpose, and then what we got, chi times chi transpose times A transpose equal to chi and chi transpose. Okay. So take transpose is the first operation, then multiply by chi is the second operation. So what we got is that this matrix is a 2m times 2m matrix, so is the same of the system order. Okay, and therefore what we can say is that your A matrix could be estimated using the same free response as chi times chi transpose to the -1, then chi times hat chi transpose, and therefore everything transpose. What we got here is that the state transition matrix A is obtained via a least square approach. Okay, so we can still use the same formulation, that is the Ibrahim time domain technique, also when the number of your sampling times is much larger than the order of your system. Okay, now that is your first case. Now let's see what's happening to the process if we are having that your number of output is less than the model order. Okay, and let's assume that your number of sampling points is equal to the model order. Okay, from the pictorial point of view, what we got is that this is the starting point. So my starting matrix, and then because of our hypothesis, what we got here is that we have just a limit number of rows than expected. So remember, we are having 2m times 2m matrix. Now what we got is an n NO times 2m matrix being NO less than 2m. Okay, so that is what we are having right now. These are the shapes of course, so chi and chi matrices there. And the same here, forgot me, yes, I forgot it. Chi and chi matrices are of that shape. Okay, what's happening here? What we can say is that both the chi matrix and the hot chi matrix are incomplete. Matrices with respect to the square dimension, okay? That is only 2 rows are available. Okay. Out of, sorry, only only NO rows are available out of the 2M rows, okay, to build your chi and your hot chi matrices. Okay, so because how can we do that? Now let's recall that the modal parameters are of course independent from the initial condition. So what we can say is that we can use additional time shift with respect to the one used to evaluate the free responses to fill in all the missing rows in order to build your chi matrices. Okay, so because modal parameters are independent from the initial conditions, okay, several additional time shifts could be used to fill in the missing rows of both chi and hot chi, of course, matrices. Okay, so specifically, the missing two M negative NO rows, okay, are obtained by introducing fictitious points, okay, from the true points by using other time shifts, okay, that is your time shifts, let's say delta T2, delta T3, up to delta T2MO. Okay, so for example, let me write your chi matrix. That should be of the shape of your starting chi matrix, like this. And then we can think to introduce all the missing lines in order to have a square matrix like this, okay, just by considering your delta T2, delta T3, up to delta T to N negative NO. So that, the resulting chi matrix is a square one, okay, whose dimensions are, of course, 2m times 2m matrix, okay, and the same for the hot chi matrix, okay. That matrix is built using the initial one that, remember, is obtained from your chi matrix 7t plus delta t1, okay, but in a number of rows that is lower than the number of columns, and then we add the missing lines, the missing rows, just by introducing delta 2, 3, delta 2, 3 up to delta t 2n negative n, 2m negative, okay, and therefore we got all square matrices, okay. Of course, now what you are having is sort of both chi and matrix are over dimensioned matrices, okay, but we have to introduce them because we need to solve the problem at least in a square form, like we have to do when taking the when taking the inversion, the matrix inversion, okay. Please note that this way of working is not that unknown to you. I just want to discuss a little bit what's happening to the very first approach that we saw together to estimate the model parameters, the approach that we saw as a single degree of freedom method in the frequency domain that we call half power bandwidth method or peak peaking method. We can use just one FRF, okay, so just one row if you want, or column of the FRM, in order to estimate your model parameters in terms of the natural frequencies and natural frequency and damping ratios, okay. Just for example, focus for a while to the behavior of just one FRF. You have just one FRF amplitude, and then as a function of the frequency, you can have several peaks of resonance. That is, you can have several natural frequencies and several corresponding damping ratios. So you have just one FRF, and then you can have several information of your model parameters, as much as they are included in your frequency range of analysis, okay? However, the Mohs shapes, of course, are just trivial one, because you know the information just one point, and therefore all the Mohs shapes will have just one unitary value, that is your let's say maximum displacement evaluated, just the only point that we know. Here comes the same way of having. For example, if you have just information on one output response, on one free response, we can have just one row that could be written when building your chi and half chi matrices. And then you, in order to have a square matrix, you can add many rows until you reach the square dimension of your chi and half chi matrix. You can have the estimate of your model parameters in terms of natural frequencies and damping ratios from the eigenvalue of your state transition matrix that you can build from these two chi and half chi matrices. But however, the information concerning the eigenvector is redundant, is not meaningful up to just one degree of freedom. That is the only one that you measure, because all the other missing lines have been fictitiously added to your chi and half chi matrix in order to build your square matrix. Okay. So that is what is generally done when we are two typical conditions. The first one is that you are having the number of rows that is, or the number sampling point that is larger than the number the order of your system, that is what is typically done, and the number of measuring points that are generally less to the number with respect to the number of model order. Okay, and that is what is generally considered. Now, in order to give an idea on how to choose your time shifts, let's have this discussion. So we have the first time shift that we call delta T1. That is the one that we need to carry on with the process, the Iberian time domain technique. Okay, then we have a number of other time shifts, let's say delta T2, 3, and so on, when we are in the case in which the number of your measuring point is less than the model order. Okay, how can we choose this? So let's see this discussion. So how delta T1, delta T2, and so on are chosen? We can write that your delta T1 is something related to your sampling time. So let's say N1 delta T, and delta T2 is equal to N2 delta T. So let me characterize these additional time shifts, delta T2, 3, and 4, as just one delta T2. Okay, so it considers all the delta T's, okay, required to fill in all the missing lines, okay, rows of kinematics and hard kinematics. Okay, just to reduce the number of symbols that we are using. So delta T2 includes all the time shifts required to solve the other problem. Okay. Of course, what we should have is that the delta T1 and the delta T set of delta T2 time shifts should be different one each other to reduce the identification issues. Okay, sorry. Okay, then another information comes from the meaning of the eigenvalue. Remember, we find out that your omega r is equal to 1 over delta T1, and then the R times function of the ratio between the real part and the imaginary part of the eigenvalue of the state transition matrix A. Okay, and if you consider the natural frequency, F is just the previous one divided by 1 to pi. 2 pi delta T1, and then the R times function of the real part over the imaginary part of the eigenvalue. Okay. So having said that, we have to consider that this function, the R times function, is a periodic function. Okay. And these R times function, the R over R function, is a function that is periodic whose values are limited by negative half pi to positive half pi. So if we are looking at the maximum value that this frequency could have, is just when we are considering the arctangent function that is equal to half pi. Okay, therefore, what we are having is the natural frequency. The maximum value of the natural frequency is just 1 over 4 delta T1. Okay, and therefore, what we are having is that your delta T1, okay, is given you by 1/4 the maximum value of the natural frequency that you are interested in. Okay, and that is the criteria that we have to consider to choose your first time shift. And then the other should be higher than by considering the set of n2 and 3 and so on that we have in this analysis. Okay, other, by considering this, other frequencies higher than this maximum value of the frequencies are translated in the zero maximum frequency range, okay, as wrong values. Okay, and you already know this problem because that is a typical leakage problem. Sorry, aliasing problem. Okay, so at the very end, what are the outputs of this analysis? First, delta T1 is chosen from the maximum frequency, natural frequency, okay, and from the sampling time, okay, and generally, of course, your delta T1 is larger, sometimes equal to delta T, but is preferred to have it larger than the sampling time, okay, prefer. Then the second output is that the free responses okay should low pass filter, okay, to remove aliasing. And remember, the maximum frequency, natural frequency, is equal to 1 over 4 delta T1. Okay? So that is what is generally considered for this approach. By the way, when we are having that the NS is your number of time instance that you know, in which you measure your response, okay, the minimum value is, of course, 2m. Okay, actually, more accurate results are gained if we consider that the number of sampling points is larger than, let's say, over the 2m. Forgot to write that optimal, when this ratio is about 3. Okay, and that is a general rule of thumb in doing that. Okay, so that's because we are introducing a sort of least square approach to solve the problem. Therefore, it would be more robust with respect to noise, and takes into account possible errors. So, in order now to answer the question of who is telling me what is the model order 2m, then we can answer to this question at the end of this approach just by considering that we start by setting this 2m value as low as possible, and then we start to iterate until we find out the convergence. So we can apply the stabilization diagram that we saw together when referring to the least square complex exponential method also for the Ibrahim time domain methods. Okay, so we start with a very low value of 2m. We make this analysis, so time shift 1, time shift 2, and so on, until we find the solution that is not dependent on the choice of the 2m. Okay, so 2m is identified from the stabilization diagram that we already saw. We're referring to the to the least square complex exponential method. Thus, your natural frequency, damping ratios, and your shape is identified. So in other words, you have to iterate for solving the eigenvector associated to the eigenvalues and eigenvector associated to the A matrix, that is the state transition. And in turn, we have to consider different dimensions of n and of m, as the model order. Okay. Before ending the class, I would like to show you what's happening when we are considering the noise effect. Okay. So, by the way, as we can synthesize the Ibrahim time domain method, requires a delta T1 for the method. In the base formulation. That is, everything is square, no special issues. Okay. Then it requires delta T2 and multiples if you want. Okay. For fictitious point. Okay. And we just discuss. Then, if noise is affecting the measure, and you are practically sure about that, then there is sort of delta T3, a third time shift for the noise evaluation. Okay, let me see now what's happening when we are considering this additional time shift for the noise. So if there exists noise, and we can see that when you are just evaluating your FRF through the analysis of the coherence function, for example, then your responses xt, free responses xt, could be rewritten as we did before in terms of model parameters to m phi r e to lambda r t, okay, plus the noise, that is the vector of nt. We can rewrite that by introducing the noisy modes, okay, or your xt could be written as summation sign r that goes from 1 to 2m phi r e lambda r t, and then we can have these equivalent model representation of the noise as summation sign from index r that goes from 2m plus 1 up to 2n, whatever it is, and then your r's noise mode e to, let's say, mu r t. Okay, and we are introducing 2n negative m, okay, noise modes. This is a definition, of course. We can say that the noise could be represented in this way as an additive form and in form of the, let's say, modal contribution, superimposition of some, let's say, noisy modes. Each one is vibrating with its own equivalent natural frequencies, but of course they are noisy, so these noisy modes and the corresponding eigenvalue, noise eigenvalue, are completely time dependent. We can't say anything about that. Okay, so one way of solving for this noise issue is to increase a lot the dimensions of the numerical model. So if 2m is increased in the estimate, noisy modes noisy mode effects can be limited. Okay, but however, why that? Because almost all modes, almost all system modes are identified. Okay, however, this way of tackling the noise problem is very time consuming and requires a high computational cost. Okay, so the idea that is interesting of identifying all the structural modes in this equation, that is just by having 2m as large as possible, is not a good one from the practical point of view. because it requires a lot of resources, computer resources, and it takes a lot of time. In order to have this identification of the noisy mode with respect to the structural one, okay, we can introduce what we call the model and alternative. Method is what we call the model confidence method, MCF. And this model confidence method, most shapes are estimated from different time shift, the one that I call delta T3 and others, okay, by comparing the most shapes are different delta T's, okay, noisy modes could be identified. Okay, so that is the approach. Now, let's see briefly how can we apply this idea. The idea is starting once again from the free responses and therefore from the kinematics. So let me focus on just one column of these kinematics. For example, what I got here is, let's say, X J, sorry, X1 of T J, X2 T J, up to the last one, let's say X and output Tj. Then we have all the other terms here, other columns that are responsible building the kinematics. Then we add some other fictitious points, okay, for example, X1 Tj plus delta T3, X2 Tj plus delta T3, up to the last one, okay, that could be X and O Tj plus delta T3. And then we have all the others once again. Okay, like this. So your general kinematics is having the double number of points that are referred to as measuring points, but half of them, the last and O lines, are fictitious points. Okay, and therefore we can call these kinematics as the one. Okay, please note once again that these fictitious points here is Xij, okay, sorry, Xi evaluated at the Tj time plus the delta T3 could be referred to the double hat component Ij of the corresponding double hat measuring point. Okay, so these responses general Tj plus delta T3 could be reviewed as the summation sign when referring to your model parameters that goes from 2 to 2m, phi r e to lambda r tj plus delta t3. That could be rewritten as the summation sign r that goes from 1 to 2m, your r mode that is now double hat, that includes the delta t3 e to lambda r tj, okay, in which your double hat r mode is equal to your r mode times e to lambda r delta t3, okay. The lambda matrix is still the same, so your components of your lambda matrix, lambda ij, are still the same, so e to lambda I times tj, okay. And therefore, what we can say is that if your psi star matrix is the one that is built using the first n o rows of the matrix, and then the other n o rows of the matrix that are the double hat one, that is a fictitious one, then what we can say is that your free responses, including in the chi-matrix, could be rewritten as we already discussed before, just by introducing the star symbol at the modal matrix, okay. Then we can introduce the additional time shift delta t1, so delta t1, in order to introduce your state matrix A, okay. And therefore, what we got at the very end, by solving for the eigenvectors of A, we are found your star eigenvector matrix by solving the eigenvector of A, that is an eigenvector, sorry, that is a modal eigenvector matrix that is having the first row that are the psi vectors, and then the other one that are the double hat vectors. Okay, now if the psi matrix and the double hat matrix are the same, that means that there is no noise at all. Okay, if the psi matrix and the double hat matrix are different, then there is noise. Okay, so that's the reason why that's the way, we are evaluating that. And in order to do that, we evaluate the modal confidence factor in terms of amplitude as the ratio between the R mode in amplitude with respect to the corresponding double hat mode R in amplitude. And we can consider also the phase of the modal confidence factor as the phase change between your R mode and your double hat R mode. Okay, best no noise if, of course, the amplitude of the modal coefficient factor is equal about 100%, so we are having the same scaling factor, and the phase of the modal coefficient factor is about 0. Okay, and therefore we iterate until we find out that there is no noise effect in your identification, and that ends the invariant time domain method. So we saw the importance for the method to introduce delta t1, fictitious points delta t2, and then for the noisy measurement delta T3. Okay, and then we found out some issues concerning this choice of these delta T's, that is time shifts that are referring mainly to the aliasing problem, and we saw how to cope with that. And therefore we define some, let's say, optimal criterion when trying to solve in an optimal way for the unification of your system in terms of polar parameters. So that's it for today. I got some minutes late. Questions? Okay, if there are no questions, thank you very much. Please remember that tomorrow there will be no classes because it's a national holiday in Italy. So we will resume the class on Friday this week. Okay, so no class tomorrow. We will resume classes on Friday. Thank you very much.